Okay, I am beginning with the numericals of Norton's theorem. Assuming that you are well versed with the theorem which was taught earlier in the previous class. So, what needs to be taken care while we are doing the numericals of the Norton's theorem? There are few similarities as I have mentioned in the previous class as well, and few dissimilarities. So similarity is the way we solve the Thevenin resistance is same as that of Norton resistance. Okay, so while calculating the Thevenin resistance, what we used to do, we used to open circuit the load and calculate the current flow into the circuit. Okay, and while if any current source is there, then we open that current source, and if any voltage source is there, then we short that voltage source or EMF source. Okay, so this is our consideration. So in the previous numericals, we have seen that if some value is written on the resistance, it is deemed to be assumed as ohms. And similarly, if some value is given and written on the voltage source, it is assumed to be volts. Okay, but in this numericals, in this numerical, if kilo ohm is given, then it is to be mentioned separately. Similarly, if the current source is given and the magnitude of the current is milliamperes, then it is to be separately mentioned clearly. Okay, so this thing is to be taken care of. Okay, so at the end, either you can again convert into SI system or you can leave as it is. Okay. Okay, so first thing first, firstly we will calculate the Norton resistance. So while calculating the Norton resistance, as I have just mentioned, what we do. So again, the purpose of the numericals of the Norton's theorem remains same, that we are required to calculate the load current. So if the load current is known to us, or the current which is flowing in the load is known to us, then we can easily calculate the drop across the load, power consumed across the load. Okay, and so this is one set of numerical or the type of the numerical which we can face. Other is the, if the numerical objective is to verify the Norton's theorem using a particular circuit, then at that time we are required to calculate the load current using the Norton's theorem, as well as by one more method of our choice. Okay, so by doing that, what happens, that if the load current is same using both the methods, then we can say that the Norton's theorem is verified. Okay, so this is the type of the numericals which we can face. Okay. Okay.
सर
So
आपने सर आपने अभी जो कहा एक बार रिपीट कीजिए प्लीज.
okay. I mentioned that either the Norton's theorem problem may require to calculate the load current across the load resistance, so that if the current is known to us, then we can also calculate the drop, and if it is known to us, we can also calculate the power consumed. This is one set of the problems which we can face. Other is the if the requirement of the numerical is such that we have to verify the Norton's theorem, then we are required to calculate the current, load current, using Norton's theorem, and also by one more method, and verify that and check that or confirm that we are receiving or we are getting the same results of the load current. Okay, is this clear to you?
Yes sir.
Now it is clear. Okay. Okay, first thing first, we will calculate the Norton resistance. So to calculate the Norton resistance, what we have to do, we have to open circuit the load, open circuit the current source, and short circuit the voltage source. And the flow of the current will be into the circuit from the load end. Okay, this is to be taken care. So taking into these considerations, current is in here. So now this is open circuit, so current will not flow here. Okay, so you can say that this is non-existence. So these two resistance will be in series, and since the current division is taking place at this node, so this 2.4 kilo will be in parallel. Okay, so we can say that 2.4 is in parallel with the series combination of 9.4 and 6.6. So in this way we can get the Norton resistance. Okay. Okay, now second step is that we are required to calculate the load current and or the short. So what we do in such case, now do we activate the current source again. We activate the voltage source again, but the load resistance is short. Okay, the load resistance is removed and it is made short circuit. Okay, current source is activated, voltage source is activated, and load resistance is short. These things are to be taken care of. Okay, so when the energy sources, current source and voltage source, are activated, then the flow of the current or the direction of the flow of the current will not be same as was used to calculate the Norton resistance. Okay, so first thing first, the current source direction or the direction of the current which is flowing out of the current source remains unaltered. Okay, so in this circuit the direction of the current is shown upwards, so the current will flow in this manner. Okay, so and there are two more loops. So we have assigned the clockwise direction of the current I1 here and the clockwise direction of the current here I2. Okay, first is the clockwise direction, and also if we go through the polarity of the 120 volt source, we can see that this is the positive terminal, so the current will flow above. Okay, although we can change the direction of the current, but it is convenient to follow this thing. Okay, because if at all the direction of the current is different, then it will we will get the result as minus. Okay, for example, if we are getting minus 5 amperes as I1 current, then we can say that okay, the assigned direction is wrong and this is the direction anti-clockwise. Okay, so at the beginning you can assume any direction, but it is preferable that you choose the clockwise direction. Okay, so in the first node here, 10 ampere is the 10 milliampere is the incoming current and I1 is the outgoing current. So the current which is flowing through the 9.4 kilo ohm resistance will be 10 minus I1. Okay, so and in this second loop, we know that I2 current is flowing above and I1 is the incoming current is in this node. I2 is also incoming current in this node. So the current I2 is flowing in this loop. Okay. So, but in this loop, first loop, the current is in this direction. This I2 is in this direction. So net resultant current in this 2.4 ohm resistance will be I2 minus I1. Okay. So, okay, clear, I2 minus I1. And now since the currents and its direction and magnitudes are known to us, we can apply the KVL in these two loops. Okay, so in the first loop, 2.4 I2 minus I1. While calculating the KVL, you can take clockwise direction or anti-clockwise direction. It is immaterial because again the sign will change if we take the undesired direction. Okay, so either we can take clockwise or based on the polarity of the battery we can take the direction. So it is here taken as the based on the polarity of the 120 volts. So the 120 volts battery is enabling the current to flow in the anti-clockwise direction. So 2.4 I2 minus I1. Now we have reached to this 6.6. So now the direction is different. Our direction was from LHS to RHS, but now KVL is being considered in the anti-clockwise direction, so this minus sign is appearing. So minus 6.6 I1. Now we reach here. So this direction is again anti-clockwise, which is favorable to us. So 9.4 kilo ohm is multiplied by 10 minus I1 and equated to 120 volts. Okay, is this clear to you, everyone? Mohit?
Yes, sir.
Okay. Now we will calculate the KVL in the second loop. So in second loop, there is not much a problem. Only one resistance and one battery source, and direction of the current is known to us. So if we take the drops in the clockwise direction, so this is the only drop which is coming across. So this is the second equation which we have reached. Okay, so there are two equations and two unknowns, I1 and I2. So we will get the values in milliamperes because each and every calculation was in milliampere. So we will get the desired results again in milliamperes. Okay. So this I2 current which was flowing in this loop is the short circuit current. Okay. So we have reached the ISC current. Now the theorem last results gives us the value of the load current which is flowing into the load when the load is placed in the original circuit again. Okay, so this is the load current which we are required to calculate. So ISC is substituted here, RN is substituted here, load resistance is already known to us, that is also inserted here. So based on these three inputs, we can calculate the load current as this. So is this clear to you? This numerical is clear to you, each and everyone?
सर
Yes.
सर इसमें सर ए बी ब्रांच में I1 करंट फ्लो नहीं होगा?
No. No. I1 current is flowing in the first loop. Okay. Okay, we will now take another numerical so that things are more clear to you. So this is the again a, now it is a simpler problem now. Here we are having only one battery source and we are required to calculate the load current using Norton's theorem. Okay. So what is the load here? 5 ohm resistance is load here. Okay. So first of all, we have to require to calculate the Norton's resistance. So while calculating the Norton resistance, this is open circuited. This load is open circuited and this voltage source is short and current will flow into the circuit. Okay, so what will happen? So when the current is flowing here, these two resistances will be in series. Okay, this is the node. So this 10 ohm resistance will be in parallel. Okay, so this circuit gives us that 10, this 10 is in parallel with the 10 plus 10. Okay, and this 20 ohm is in series, so we will add this. Okay, so in this way we can get the Norton's resistance as 26.6 ohms. Now we are required to calculate the short circuit current and the load current. Okay, so same process is followed. Load current is removed and it is replaced by a short circuit, and battery is enabled. Now we will calculate the current which is flowing. Okay, so current will be flowing in this manner. In first loop, 10I is the current, and at node B, current division occurs. So I1 current is flowing in the parallel branch. So the current which is flowing through this 20 ohm resistance will be I minus I1. Okay. So in the first loop, we can see that this is the 10I current, this is the 10I1 current, and this is again 10I current, because this is the I current which is flowing. So this is equated to 100 volts. And in the second loop, what is happening? In the second loop, there is no battery source. Okay, so when there is no battery source, but we know that these 10 ohm and 20 ohm resistances are in parallel. So when they are in parallel, it means that the voltage drops across them will be same. Okay, so either you can apply the KVL or you can apply the drop formula. So if you are using the drop formula, you can simply write that okay, 10I1 is equal to 20I minus I1. Okay, either you can do this, or if you are applying the KVL, then it means that EMF across the closed loop is equal to the drops in the circuit. Okay, so you can take any direction, either clockwise or anti-clockwise, doesn't matter. So if you are taking the clockwise direction, then this is 20I minus I1, the drop across this resistance. Now the direction of the current in this resistance is towards down or in the opposite manner. So we get minus 10 I1 and equate it to 0. So we will get the relationship between the I and I1. Okay. So again, there are two equations and two unknowns. So we can calculate the values of I and I1. Okay. So what is the short circuit current? Short circuit current is I minus I1. So since we have calculated the I and I1, we will calculate the short circuit current as I minus I1 and 1.25. Now we can apply the Norton's formula for load current calculation, which is this as shown. So using this formula, we can calculate the load current. Okay, short circuit current we have just calculated. Norton resistance we have calculated. Load resistance is known to us as 5 ohms. Okay, in the original circuit. So we will substitute these values to get the load current. Okay, so is this clear to everyone?